Okay, let's see what our example says. A thin flexible wire has one end fixed at the origin. So here we go. And the other at another point with coordinates little b and big B. So this red curve is our wire. A bead of mass m is threaded onto the wire and it is able to slide along the wire with no friction. So we are assuming no friction. The only force that is actually acting on this is gravity, downward. The only force that is acting on the bead is the force due to gravity. Awesome. The bead is released with initial velocity 0 from the origin, and it slides along wire under the force of gravity until it gets to the endpoint with coordinates little b comma big B. All right, so far so good. And then let's see what the problem is, what the question is. Which curve leads to the fastest time of descent? Folks, let me scroll up here. This is a beautiful problem. You can imagine variety of shapes that connect the origin to the fixed point with coordinates little b comma big B. Here I drew one of them. This red curve is one curve, one of the curves that connects the origin to the point with coordinates little b comma big B. But there are a variety of other curves. No, the question is that if we assume that the bead is sliding due to the force of gravity, the only force that is being applied to the bead that causes the motion of the bead is gravity, what should be the shape of this wire to make sure that the amount of time that it takes the bead to travel from the origin to the point with coordinates little b comma big B is shortest? We want the least amount of time. This is a beautiful problem. So what shape should the wire be in order for the bead to complete its journey in as little time as possible? And I can imagine that you may immediately say it should be the straight line, right? That may be our initial guess. Maybe the straight line that connects the origin. If the shape of the wire is a straight line that connects the origin to the point with coordinates little b comma big B, that will give us the least amount of time for the bead to travel from the origin to the point b comma B. And the surprising answer is that no, that will not be the case. We will carefully analyze this problem. I will tell you what the correct answer is. The correct answer is not the straight line. To your surprise, it is not the case that if the wire has the shape of a straight line, then that will correspond to the least amount of time for the bead to travel from the origin to the point b comma B under the force of gravity. And this is really interesting, and we want to talk about it. Okay, so what I want to do is that let me first share a few remarks, comments about this problem, and then we will dive into the solution, how we should solve this problem. So I'm going to start by making some remarks. So my first remark is that historically, this problem actually played an important role in the development of calculus of variations. Let me write this. Historically, this problem, the problem of finding the least time curve, the least time curve for the journey of the bead, this was a big problem. I again recommend that you Google this. Google this problem and see the history. That's a beautiful history. This problem played an important role in the development of the calculus of variations. Okay. And now, actually, let me tell you what the solution is. We will do the work. I will definitely show you what the differential equation is that governs the shape of this least time curve. However, I just want to make sure that you know that the solution will not be the straight line. The solution, by that I mean the shape that allows a bead to slide from one end to the other in the shortest possible time is not a straight line, is an arc of something which is called the cycloid. Now, again, I'm not going to spend time explaining carefully what a cycloid is. That this itself is an interesting curve. Please do a little bit of research about cycloid as well. But it will look like this. The shape, the curve that gives you the least amount of time, it will look like this. It's this part of a cycle. This is what I drew here is one arc of a cycloid. It's part of this cycloid. And just again, I recommend that you do the research, but the cycloid is the curve traced by a point on the circumference of a rolling circle. So consider a circle and pick a point here and assume that this circle is rolling, right? As it is rolling, this point is moving, right? And this point will trace out a curve. That curve is a cycloid. And the solution to this problem also will be a cycloid. So let's say this is, for example, your origin, and this is the point B, comma B. This curve, which is part of a cycloid, will give you the least time curve. Or so that is the solution. I just told you about the future, what the solution will be. And also one quick comment about the name of this problem. I called this problem the Brachistochrone problem. And let me make a comment about this. The term Brachistochrone comes from the Greek words brachistos, which means meaning the shortest, and chronos, meaning time. Or so now that I made my comments, let's actually see how an ODE comes into play when we want to solve this problem. So among all the curves that are connecting the origin, all these, by curve here, I mean graph of a function that connects the origin to this point B, little b, comma, big B, I'm looking for the curve that gives me the least amount of time for the journey. So let me write solution to our problem. So that the first thing that I will do for you, I will tell you that this problem can be mathematically described as a minimization problem, minimization of some functional. That will be the starting point. And then you will see that when we want to minimize the functional, that will correspond to an Euler-Lagrange equation, which is a differential equation. So let's introduce our symbols, the quantities of interest. So obviously the main quantity of interest will be this big T. Let big T be the time required for the bead to slide from the origin to the fixed point with coordinates little b, comma, big B. Let me actually draw a picture here again. X-axis, Y-axis, and then here we go. This is little b, comma, big B here. And then the t is the time required for the journey. And now I'm going to introduce two other symbols that will be useful. So I'm going to introduce little s as the arc length. The arc length, the distance traveled, the arc length, the distance along the curve, the arc length along the curve, measured from the initial point, the origin, the initial point, 0, 0. And I'm gonna call the full length traveled the big S. Big S, the total arc length of the curve. The total length traveled, maybe that's a better way to say this. The total length traveled along the curve from 0, 0 to little b, comma, big B. So the way I introduce everything, at this point, at the origin, little s is 0, and our time is 0. And when we arrive to this point, here, little t, the time will be big T. This is the time required for the entire travel. And the arc length is equal to big S. That is how I did this. So no, what we want to, among all the possible purple curves, I want to find a curve that minimizes big T. So how do I think of big T? This is the way we're gonna attack. This is, I think, is very interesting, creative, beautiful. I wanted to find a formula for this big T, and the way we will do it is as follows. We say that this big T is the integral from 0 to big T of dt. This is just a fundamental theorem of calculus, no question about this. Integral from 0 to t of 1 dt, this is 1 dt, right? Let me write 1. It is equal to little t as it varies from 0 to big T, and that will give us big T. So no question about that. And now, what I'm gonna do is that I'm gonna use like a change of variable in a sense. I'm gonna write this as integral. This is like a substitution. I'm gonna write this as integral from 0 to t dt ds. Okay? I'm gonna consider little s as my variable. And my friends, and hopefully you know this, the derivative of the arc length traveled with respect to time is the magnitude of the velocity vector of this bead. Magnitude of the velocity vector is a speed of this bead. Magnitude of the derivative with respect to time, the derivative of the distance traveled along the curve with respect to time is the magnitude of the velocity vector. I can actually explain this in a more precise manner, but I think this is good enough at this point. And velocity vector of the bead. So I'm gonna call this v. I'm going to denote this little v. Little v, this is like the speed, the magnitude of the velocity vector. So if ds dt is little v, dt ds will be 1 over v. And again, here also we are using a little bit of calculus because ds dt is not really a fraction. So I'm using a little bit of calculus, thinking about inverse of a function and the chain rule and so on and so forth. Since ds dt is v, dt ds will be 1 over v. So this is integral from 0 to t of 1 over v, the magnitude of the velocity vector, ds. All right, so far so good. Now, I realized that I made like a small mistake here. And when I used my substitution, when I changed the variable, I have to also change the limits of integration. I didn't change my limits of integration. So for the limits integration for little t are 0 and big T, the limits of integration for little s, as we discussed, we start with little s equals 0, and we end up with little s equals big S. So I should have put big S here. Big S, big S. Okay, so far so good. Now, what we know about this infinitesimal arc length, ds, right? Again, I really hope that you remember this from calculus. I will make a quick comment about this as well. But the hope is that you remember this from your calculus courses. Recall from calculus that ds is a square root of 1 plus y prime of x squared dx. Now, just a very small comment about this. So you can, let's say that this is your curve. You can think of dx as an infinitesimally small delta x. dy is a very small delta y, and this is your ds. Now, if everything is really small, the length of ds is the same as the length of this line segment, this chord. So here we have d using like we have a right triangle. So ds squared will be equal to dx squared plus dy. This is not a careful argument. We can make these things very precise. Most likely you saw a more precise argument in your calculus course, but this is just one way to remember what's going on. At least you can think of it as a way to remember what's going on. So ds is equal to a square root of dx squared plus dy squared, and then you can factor out dx squared. You will get a square root of 1 plus dy over dx squared times dx, which is the formula I just wrote. Okay. So we know what ds is. So the conclusion is that this t, the total time required for the travel, is equal to integral of 1 over v, and ds is a square root of 1 plus y prime of x squared dx. And now that I'm integrating with respect to x, I need to use the limits of integration for x. Now look at our picture. What are the limits of integration for x? The x coordinate here is 0. The x coordinate here is little b. So I'm gonna use 0 and b. 0 and b. Folks, this is the quantity that I want to minimize. Among all possible y of x's that connect the origin to the point little b, big B, I want to find the y of x that minimizes this expression. Okay? Now, the expression that we have here, it also involves this magnitude of the velocity v, our speed. How can I find the v at any level, at any portion of the like motion? I want to know what the velocity is. So I need to find an, in order to move forward with this, I need to find an expression for v. And for that, I'm going to use a very important principle from physics. I'm going to use the principle of conservation of energy. The sum of kinetic energy and potential energy is conserved. That is how I will find an expression. That is one way to find an expression for this v. So let me continue my solution. The next objective for me is to find an expression for this v to have a better idea of what this functional is, this t. Now I'm looking at t, I want to look at t as a functional that involves y and y prime, and then I will minimize this functional. So to obtain an expression for V, we can use the fact that the total energy is conserved. We can use the fact that the total energy is conserved. Okay, so what does that tell me? So let's say, let me draw our picture again. This is our wire. And what I want to do, I want to know what the velocity of the bead is at any point there as it is sliding along this wire, right? So what I will say is that if you give me any point with coordinates y and x, the total energy here must be exactly the same as the total energy at the origin, right? So I'm gonna write the kinetic energy. So let's say that it is at this point at time t. At time t. Here we are at time 0, at time t equals 0. So the kinetic energy at t greater than 0 plus the potential energy due to gravity. Here the force in that is playing a role is gravity energy at t greater than 0 must equal the kinetic energy at t equals 0 plus the potential energy at t equals 0. So what are these quantities? My friends, for the potential energy due to gravity is mgh. What this h is, you have to choose a level as the level of 0 potential energy, right? What I'm gonna do, I'm gonna consider this level, the level where the bead is at time t equals 0, this level as the level of 0 potential energy. It doesn't matter where you consider is the 0 potential. It doesn't matter. What really matters is the difference between the potential energies. The 0, where you consider the 0 level doesn't matter. If you do that, then this quantity will be 0. At time t equals 0, the potential energy is 0. Also, the statement of the problem says that the velocity of the bead at t equals 0 is 0. It says that the bead is released from rest. So this is the velocity of the bead at t equals 0 is 0. This is also 0. Okay, so far so good. Now, what about the kinetic energy of the bead at t greater than 0? So if the speed is v at this point, I wanted to find this v. The kinetic energy is 1/2 mv squared. What about the potential energy if this height is y and is moving downward in the direction of gravity? So the potential energy is negative mgy. If it was moving in the opposite direction of the gravitational force, that would have increased the potential energy. But here we have a decrease in potential energy due to gravity. So what does this tell me? This tells me that when 1/2 mv squared is equal to mgy, and then obviously m and m, they cancel. This tells me that v is equal to a square root of 2gy. This is great. And why did I use the plus sign? I'm looking at v as the magnitude of the velocity vector. We are like considering this case that the s is an increasing function, ds dt is positive. And this is the magnitude of the velocity, so I didn't write minus the square root of 2gy. Or so now we have an expression for v. When you are at the like level y in the vertical direction, the velocity is a square root of 2gy. So let me call this 2, and then I'm gonna combine this with 1. So I had 1, an expression for the total time, and now I know what v is. So 1 and 2 together, and 2 together, they tell me that t of y, t as a function of y, is equal to integral from 0 to b, a square root of 1 plus y prime of x squared divided by v, which is a square root of 2gy dx. And of course, 2g, g is acceleration due to gravity, is a constant number, 9.8 something. We can assume that is a constant number in this problem. I can bring it outside the integral. T is equal to 1 over a square root of 2g, integral from 0 to b, a square root of 1 plus y prime of x squared divided by a square root of 2gy dx. So this y is a function of x. So among all functions y of x that connect the origin to the point with coordinates little b comma big B, I want to find the y of x that minimizes this quantity. I want to find the y of x that minimizes this quantity. So this is 1 over a square root of 2g is some constant number. That doesn't change anything. So the what we want to minimize is this guy. That is what we want to minimize. So let me write, so thus our goal is to find a curve y of x connecting the origin to the point little b comma big B that minimizes integral from 0 to b of f of x comma y prime dx, where, so I gave a name. Well, folks, I didn't do anything weird. I just gave a name to this expression. This is an expression. It involves y and y prime. You can view it as an expression f of x comma y prime, where f of I wanted to like make this analogous to the theorem that we discussed in the previous video. F of x comma y prime is equal to a square root of 1 plus y prime squared divided by, I just realized that I had a typo above as well, divided by a square root of y. When I brought out this 2g, I shouldn't write 2g here anymore. I brought out the square root of 2g, I put it in the front, so on the bottom we only had a square root of y. So this is what you if you want, you can call this your I of y. This is the functional that you want to minimize. And that is your f. In this example, the expression that you have inside the integral is a square root of 1 plus y prime squared divided by square root of y. It is an expression in terms of y and y prime. You can view it as an expression in terms of x and y prime. It doesn't matter. So then now what do we know? Now that we want to minimize this function by the theorem that I discussed previously, we have to solve the Euler-Lagrange equation by what we previously discussed, by what was discussed previously, the curve y of x that minimizes the functional I, that minimizes the functional I, must satisfy the corresponding Euler-Lagrange equation, the corresponding Euler-Lagrange equation. And what is that? We went over this before. d dx of partial f partial y prime must equal partial f partial y. Okay, let me compute these quantities, the quantity on the left, the quantity on the right, and then you will see that, yes, we will have a differential equation. It's going to be a little bit of tedious work, but it's worth it. I want you to see that final differential equation whose solution will be a cycloid, as I promised. Okay. So here we have let me write the expression for f again. So we're going to use it repeatedly. So we have f of x comma y prime. Here f is just only a function of y and y prime. That's okay. You can write that is like a simpler case. So it is a square root of 1 plus y prime squared divided by a square root of y. And now what I will do is that first I will compute this quantity, and then I will compute that quantity, and then I will also take the derivative of partial y prime. We have starting with partial f partial y prime. Partial f partial y prime is equal to partial y prime of a square root of 1 plus y prime squared divided by a square root of y. When you are taking the derivative with respect to y prime, we are treating y and y prime as independent things. So s1 over s square root of y is a constant. I can bring it out. I will have partial y prime of a square root of 1 plus y prime squared. Okay, this is a good practice for calculus, like refreshing your memory of rules that you learn in calculus. My friends, remember that by the chain rule, I know that every time I have a function u and I have a square root of u, I want to take the derivative, it will be equal to u prime divided by 2 square root of u. This I know from calculus. So I'm going to use my rule. So I have the 1 over a square root of y is outside. I'm going to keep it outside. And then the derivative of the inside, that is u prime, derivative of the inside will be 2y prime, because I take derivative of y prime squared with respect to y prime is 2y prime. And then in the numerator, 2 square root of u, 2 square root of 1 plus y prime squared. 2 and 2's cancel. We will have 1 over a square root of y prime divided by a square root of 1 plus y prime squared. Awesome. Now, what about partial f partial y? Very soon I will compute ddx. I will compute ddx of partial f partial y prime very soon. But let me first compute partial f partial y. This is equal to partial y of a square root of 1 plus y prime squared divided by a square root of y. And since we are taking the derivative with respect to y, a square root of 1 plus y prime squared is a constant. I can bring it out and then take the derivative of 1 over a square root of y with respect to y. So again, from calculus, I remember that if I have 1 over u, where u is a function, and I want to take the derivative with respect to the independent variable, by the chain rule, that will be negative u prime divided by u squared. So I'm gonna use this rule. So it's a square root of 1 plus y prime squared is outside. I'm gonna keep it outside. And then here I should write negative derivative of a square root of y, which is with respect to y, which is 1 over 2 square root of y. And then the denominator squared, a square root of y squared is y. So this will be equal to negative 1/2. And then we have a square root of 1 plus y prime squared. And then we have y square root of y. Or that is partial f partial y. And now I want, so now that we have this, so what is the differential equation that we need to solve? So let me write this. I will continue my calculations for the left-hand side, but let me rewrite what we are doing, making sure that everybody is following what's happening. So the minimizing curve y of x is a solution of the differential equation The minimizing curve, I mean the least time function y of x. So the d dx of partial f partial y prime, d dx of partial f partial y prime. Here is partial f partial y prime. d dx of 1 over a square root of y prime over a square root of 1 plus y prime squared. This must equal to partial f partial y. Where is partial f partial y? I have it here. This is the Euler-Lagrange equation. Negative 1/2 a square root of 1 plus y prime squared divided by y square root of y. This is your differential equation. The unknown is y as a function of x. Of course, you can leave it like this, but I'm going to simplify it. I want to take the derivative that we have on the left. Ultimately, we get like the ODE that looks much simpler than what you see here. We can simplify the left-hand side, LHS, as follows. So let's actually take the derivative. Again, this is a good practice for our calculus skills. d dx of, what do we have? We have y prime divided by a square root of y times 1 plus y prime squared. I want to take this derivative. So what do I do? I'm going to use the quotient rule. Derivative of the numerator times the denominator minus numerator times the derivative of the denominator. The denominator is y times 1 plus y prime squared, the whole thing to the power of 1/2. A square root is to the power of 1/2. Divided by denominator squared, y times 1 plus y prime squared. Okay, this is all very good. Now, this is equal to y double prime times a square root of 1 plus y prime squared. So far, so good. Minus y prime. And now I'm going to take the derivative of this quantity to the power of 1/2 with respect to x. So I'm going to use the power rule and the chain rule, all of them together. So y prime. The exponent comes here, and then I will subtract 1 from the exponent. So this is like the derivative of the outer function. And now I have to take the derivative of the inner function. Y times 1 plus y prime squared. Divided by y times 1 plus y prime squared. Okay, so far so good. This is equal to y double prime times a square root of y plus 1 prime squared. No question about that. And then this part, I can put everything together as a quantity to the power of negative 1/2 is like 1 over the root of that quantity. So I can rewrite this as minus y prime over 2 a square root of y times 1 plus y prime squared. That was the highlighted part. And now I'm gonna take this derivative. That's the next job for me. I'm gonna take the derivative using the product rule. Derivative of the first term times the second term plus first term times the derivative of the second term. Derivative of 1 plus y prime squared with respect to x is 2y prime y double prime. And then everything divided by y times 1 plus y prime squared. So what is this equal to? So 1 by 1. I'm going to start with this. This guy, I have a square root of a quantity on top, that quantity on the bottom. That gives me the square root of that quantity on the bottom. A square root of t divided by t is equal to 1 over a square root of t. That is what's happening for that term. So I will get y double prime divided by a square root of y times 1 plus y prime squared. All right. And now I'm going to focus on this part. This part. Okay, let's see what we have here. This 1 plus y prime squared and 1 plus y prime squared, they cancel each other. We will have y prime squared on top, 2y on the bottom, and also we have the square root part. So this will give me minus y prime squared on top, 2y, and then this square root part. A square root of y times 1 plus y prime squared. Okay, excellent. And finally, what about this part? This part, I'm gonna have minus sign, and then we have y prime and y prime. That gives me y prime squared, and also I have a y double prime. That gives me y double prime. What about the y? The y here and the y on the bottom, they cancel each other. So what remains is this square root part and this part in the denominator. So I will have a square root of y times 1 plus y prime squared, and then times 1 plus y prime squared. Okay, we are just simplifying the left-hand side of the Euler-Lagrange equation. And now I can factor out. I can factor out 1 over a square root of y times 1 plus y prime squared. The first term gives me y double prime. The second term gives me y prime squared over 2y. The third term, what remains is y prime squared y double prime divided by 1 plus y prime squared. Now, folks, focus on this guy and that guy. Let me simplify the highlighted part. So this is equal to 1 over a square root of y times 1 plus y prime squared. That is good. And then I'm going to keep this part. This I'm not going to do anything with it. But for the highlighted part, I'm going to do the common denominator. 1 plus y prime squared, and then y double prime plus y double prime y prime squared minus y prime squared y double prime. This is the highlighted part. This is the highlighted part from above. And of course, you immediately see that this guy and that guy, they cancel. So what we will have is 1 over a square root of y times 1 plus y prime squared times negative y prime squared over 2y plus y double prime over 1 plus y prime squared. A very good practice for your calculus skills. This is the left-hand side of our Euler-Lagrange equation. So we can rewrite our Euler-Lagrange equation as follows. Equation as follows. What do we have on the left-hand side? I just figured it out. On the left-hand side, I have 1 over a square root of y times 1 plus y prime squared times negative y prime squared over 2y plus y double prime over 1 plus y prime squared. What do we have on the right-hand side? On the right-hand side, we previously discovered on the right-hand side of our Euler-Lagrange equation, we had negative 1/2 a square root of 1 plus y prime squared divided by y square root of 1. Or so how can I simplify this? Let me multiply both sides by this guy so that I get rid of this in the denominator. Multiply both sides by a square root of y times a square root of y, let me write it like this, times a square root of 1 plus y prime squared. It will be clearer what's happening if I write it like this. To get, on the left-hand side, we will be left with negative y prime, the bracket part, plus y double prime over 1 plus y prime squared. On the right-hand side, the square root of y and the square root of y, they cancel each other. The square root of 1 plus y prime squared times the square root of 1 plus y prime squared, that just gives me 1 plus y prime squared. So it will be 1 plus y prime squared divided by y. All right, very, very good. So actually, let me bring the first term to the right-hand side. So y double prime divided by 1 plus y, to simplify this a little bit further, this will be equal to negative 1/2 1 plus y prime squared over y plus 1/2 y prime squared over y. I just brought this term to the right because it has 1/2. The other term on the right also had 1/2. So I can factor out 1/2. So that means that y double prime divided by 1 plus y prime squared is equal to negative 1/2 1 plus. Okay, we can factor out this negative 1/2. Or let me factor out positive 1/2. Positive 1/2, negative 1 minus y prime squared plus y prime squared divided by y. Yeah, that is exactly what I will get. And that will tell me that y double prime over 1 plus y prime squared is equal to negative 1 over 2y. If you write, you can rewrite this as, so cross multiply 2y y double prime plus 1 plus y prime squared is equal to 0. This is our Euler-Lagrange equation. The least time curve satisfies this equation. It's a solution to this equation. Here, I'm not going to go over how you can actually solve this equation. This is a nonlinear second ODE. If you solve it, you will see that the solution is part of a cycloid, nonlinear second order ODE. All right, folks, as you noticed that there was a little bit of tedious work to simplify the Euler-Lagrange equation. I just want to make this comment that there are like tricks, clever things that one can do to make the calculations less tedious. In particular, in this problem, if you view x as a function of y instead of viewing y as a function of x, when you want to write the functional I, the t, the total time big T, then things will become a little bit simpler to manage. But nevertheless, we considered y as a function of x, and now we have our Euler-Lagrange equation. It's the second order ODE. So as you can see, Euler-Lagrange equation can be a source of some of the ODEs that appear in real life applications.